Thank you so much, Radigo. And today I'm really excited to share our work with you on building flexible, low-cost wireless access networks with Magma. This is joint work with many people, including some colleagues at Databricks, Systems Approach, Princeton, and a bunch of folks here at Meta, and this is where we started the project. And despite the long author list, there's a bunch of other people to thank, including the broader Meta connectivity team, some of our partners at FreedomFi and Access Parks who provided the deployment data I'll be talking about, the Linux Foundation, who stewards the project today, our early deployment partners, Telefonica, Croton, Brick, and MuralNet, as well as the broader Magma developer and user community. And I also want to give a special shout out to my co-authors, Amar, Padmanabhan, and Bruce Davie for some of the slides and figures in this talk. So in the next room over right now, they're talking about real networks, but I want to claim to you today that cellular networks are in fact the most successful real networks in existence. They cover about 97% of the world's population, and 5 billion people and 20 billion devices are transferring 100 exabytes of data per month on these networks. It's hard to know this for sure, but I would guess that these are probably the primary way that most humans connect to the internet. But despite the success, there's still a number of gaps. So if you look at some data according to the GSMA, and we focus for a second on mobile broadband data, or mobile broadband service, in 2017, there was something like a 10% coverage gap. So these are people who live outside the coverage area of what were at the time the modern networks, 3G and 4G, providing broadband services. And there was about a 45% usage gap. So people who lived within coverage of these networks but were not using them for whatever reason. If we fast forward to the most recent year that we have available and we start looking at 4G and 5G networks, these numbers haven't actually changed much. And according to the GSMA, most of these networks are reaching, using traditional approaches, the limits of commercial viability. And what this means is that rural areas are remaining chronically underserved and urban areas are remaining really expensive. And so if you wanted to sum up why this is the case, then the short version is rural areas have lower return on investment for network operators. And in urban areas, operators are facing rising costs to cope with this 100 exabytes of data per month that's being transferred, and there are various structural barriers to entry that reduce competition. So when we started this project, our question was really, how can we reduce costs, enable competition, and on a tertiary basis, also improve the reliability and scalability of traditional cellular cores? And what we did is we took inspiration from places where there's internet beyond the cellular edge. And I want to give you an example from one of our early deployments of our system in Peru. And so most of the population in Peru is concentrated along the coast, but if you drive about 16 hours inland, you'll get to this town called Pucallpa, which is at the beginning of the Peruvian Amazon. And if you're an infrastructure nerd like me, you'll notice that Pucallpa is a sizable town, but it has way more radio towers than you'd expect. And one of the reasons for this is it's at the end of the road and therefore the end of the fiber. And many of these radio towers belong to small ISPs who are taking fixed internet connections from there and providing wireless service into towns beyond there. And so we worked with an ISP called Air One, and this is their central office in the outskirts of Pucallpa. This is what their network core looks like. They're taking, again, the business class cable services that are available in town. They're sending it up to that tower that I showed earlier, and using microwave relays of lengths around 40 to 40 kilometers or more, sending internet service to towns like this one, Puerto Bermudez, which is now about 200 kilometers beyond Pucallpa. And in Puerto Bermudez, Air One and another ISP that plays a similar role provides service, the only internet service in town, via Wi-Fi on the last mile. So you'll have another microwave relay from their central tower to the top of your house. You'll drop a cable inside and you'll get Wi-Fi indoors. And so this is, again, the way that the internet gets delivered beyond the cellular edge. And if we pause to think for a minute, it's a little weird that why does Air One use Wi-Fi to provide service in this extremely rural environment when cellular networks in many ways seem like they might be a more appropriate fit? Right, so from a last mile perspective, a cellular base station can provide coverage over 1 to tens of kilometers potentially. For an ISP, it's a much more scalable radio infrastructure, and you can support really complex QoS policies, which might be nice if you want to sell those kind of services to your users. But the reason that Air One and even other small ISPs like Air One providing low-cost service in urban areas use Wi-Fi is because it has a low barrier to entry. If you want to deploy a single LTE or 5G radio, you have to deploy an entire packet core. And this is really complicated. It's expensive. For those of you who work in cellular, you have to learn a completely new set of acronyms and vocabulary. And fundamentally, Air 1, a small rural ISP, would be stuck with a network architecture that was intended for large nation-scale network operators who have the resources and had the network expansion plans to justify amortizing this cost and complexity across their network. And so we kind of proceed from this insight that the choice of radio technology an operator wants to use in their network should not define the operator's network architecture. And that's what we tried to do with our system. So as many of you may know, traditional cellular relies on centralized core networks. And this is the case in whether you're using LTE or whether you're using 5G. And while you can clearly build successful networks with this network architecture, you run into a number of challenges. First, traditional cellular cores leak state across elements, and it makes it really complex to reason about their behavior and to upgrade and change them. So if we have a single device that's connected to the network, there's going to be state associated with that device replicated across every single core element in the network, keeping track of the fact that it's connected. We have to make sure all of these elements are synchronized with each other, and we have to keep track of this state for every single UE that comes onto our network. Similarly, traditional cellular cores leak information about the radio into the core. And so if you have already deployed an LTE network, you have a cellular LTE core, LTE radio, and you want to add one 5G radio, you have to deploy a completely separate core, even though these two cores are providing functionally equivalent services in many cases. And to give you an example, if you have two UEs who want to connect to your network in both cases, they're going to be using different interfaces and different messages for functionally equivalent procedures, and this information has to be exposed to all the elements along the core that are handling this attached message. Even worse, these elements have to know that a GUTI coming from the S1 interface has different syntax and semantics as a GUTI coming over the N1 interface, and you have to interpret them differently. So we might ask ourselves, like, why do operators put up with this? This seems like it would make no sense. First off, they want to use cellular radios for their network, and so if you want to do that, this is the only game in town. But you also want to support rich policies in their access networks, and so it's useful to have some of these kind of more complex systems sitting in your core so you can provide fine-grained authentication and, more importantly, bill users for their services. They also care about mobility, which is easier to implement in a centralized way, but we'll come back to this. And one kind of side point I want to make here, it's almost if we think about these design principles of the DARPA internet, like what Clark talked about, it's almost as though if you started from the bottom, prioritizing accounting for user traffic, you would eventually wind back up at a cellular architecture. So it's very different than what the internet looks like. And in many ways, it also reminds me of like the bad old days before we had SDN, where if you wanted to implement complex network policies, you would kind of arrange middle boxes on your path to make sure that your policies were being implemented in the way you saw fit. Now, we've largely solved these problems in the data center. We kind of know some general techniques for approaching this. We can separate out a policy-rich software edge from a fast and simple fabric, and we can add manageability to our network through a logically centralized control plane. And so this is what we tried to do with Magma. We tried to take this same approach and bring it to the cellular core. So we want to have a distributed network edge and a centralized controller while maintaining the existing RAN infrastructure that we'd like to use. So in Magma, we think about our distributed edge with kind of two as the elements that are facing the legacy pieces of the network. So the radio elements that we care about, as well as any legacy core network elements, or potentially even other network operators that we want to interface with. We introduce two new elements, access gateways and federation gateways, that will be implementing our distributed network edge. And we implement a set of cloud-based kind of microservices to manage this whole system in what we call the orchestrator. And the access gateways and the federation gateway continue to support our standard interfaces because we want to take advantage of the rich ecosystem of radios and user devices that already exist in the cellular world, and we want to be able to connect to existing network operators. And for the purposes of this talk, I'm just going to focus on the access gateways because this is frankly where most of the action is, but a lot of the principles that we can see in how we design these apply elsewhere. So in Magma, we have one access gateway per cell site, as opposed to one centralized core for many different radio nodes. And so in an access gateway, the data plane, so users' traffic, goes directly to the internet, and the control plane for the access gateway goes to the orchestrator. And depending on what kind of cellular radio that you want to connect, you can use any of these access gateways. If we zoom inside an access gateway, it kind of divides into two parts. On the left side, we have RAN-specific protocols that implement and terminate the control plane from 3GPP. So if you have a 5G or an LTE radio, all those legacy protocols are terminated on the left side of the access gateway. And on the right side, we implement protocol agnostic network services to help us implement those rich network functions that we still want from our core network. For the data path, we use a software data path, in our case OVS, that is configured by the data plane configuration module to implement whatever policies that we care about. And I just want to note here that while we happen to use OVS and we happen to build off of the open air interface core originally, there's nothing fundamental about these RAN specific or data path choices. You can implement whatever data path or EPC 5G core that you like. So now that we move to an architecture like this, we've also introduced some new challenges, right? So we've built ourselves another distributed network. So we need to ask ourselves how we manage state in this distributed environment, and also how we manage the control plane. So like many production software-defined networking systems, Magma implements a hierarchical control plane. And we define this hierarchy based on the state that we care about, as well as the timescales on which it changes. So in Magma, there's really two kinds of networking state that we care about. There's configuration state, which changes on human timescales, and these are things like which users are allowed to connect to our network and what rate policy should be applied to that user's traffic. This is managed by our global control plane in the orchestrator, and users, or network operators, modify this state using the REST APIs exposed by the orchestrator. Conversely, runtime state changes on network timescales, and this is like what is the NAS state of the UE, or what percentage of a user's data quota has a user consumed. And this is managed by our local control plane. This state is ephemeral, it's recoverable, and it's stored in the access gateway. And so again, to see kind of how this breaks down, our local control plane corresponds to those protocol-independent network functions I was talking about earlier, and the global control plane is the orchestrator. And if for whatever reason the access gateway goes down, or we have to restart it, a phone in the worst case is going to reconnect, and it will kind of that runtime state will be reestablished. So when we take this approach, we have a number kind of implications that we come away with, right? So we've achieved one of our goals of abstracting away the radio access network, and we've solved this problem of state leakage that we have in traditional cores. We've modularized the network edge, so we now can have a really simple IP fabric connecting all of our base stations together, and we don't really have any choke point devices anymore. We've achieved better scalability properties since we can scale our core capacity with our RAN by simply adding more access gateways, which each individual one is quite cheap. But we also gain this really nice benefit of the ability to scale down. So the simplest Magma network is just a single access gateway and an orchestrator. And so it makes it easy to start small and grow your network from there. There's also some good properties for how we can think about managing faults. And so as folks may have experienced potentially, nation-scale outages do happen somewhat regularly in traditional cores. If you have a fault in your centralized core, you can take down the entire country's mobile network for a given operator. But this is pretty hard to do in Magma. If we have a single access gateway go down, the rest of the network continues operating unaffected. It just affects the towers that are managed by that access gateway. And similarly, if we were to lose the kind of the global control plane in the orchestrator, while we wouldn't be able to do things like provision new users into this network, the local control plane that's running on each access gateway would still be able to handle things like users arriving to the network, connecting for the first time, and so forth, as long as they'd already been configured by the orchestrator. So let's talk about how we evaluated Magma. And so some of the key questions that we asked were whether Magma is able to handle realistic workloads, whether Magma can achieve our goal of reducing the costs of deploying wireless access networks, and whether Magma can support large-scale production deployments. So since Magma is an open source project, our team doesn't actually run any networks directly. So for our evaluation of the paper, we used network emulation. We used some commercial test equipment called Spirant Landslide, which can basically simulate arbitrary configurations of RAN and UEs. We deployed our access gateways on both a virtual as well as bare metal form factor. And I want to note that this bare metal access gateway is typical hardware used for real production deployments. It's a quad-core x86 fanless single board computer. It's available on Amazon for $370. And so one insight as we're thinking about whether Magma can handle real traffic is thinking about what is the load that a single access gateway has to manage. And it turns out to be limited by the radio access network, right? So the typical eNodeBs that we see used in the deployments that we're aware of handle about 100 active users and maybe about 150 megabits per second. And this is driven by limitations of the channel width, right, that the eNodeB supports. So this is on a 20 megahertz channel, which for LTE is about as wide as you see in practice. And obviously, you can scale up your access gateway if you need to support more capacity. We have some details about that in the paper. But for this emulated, kind of fully saturated, traditional, kind of typical deployment of 3 eNodeBs on a tower, providing 3 sectors of 360-degree coverage in a single access gateway, we see that even our low-end bare metal access gateway can handle that load with no problems. So as users connect, the control plane load on the CPU load as we're handling connections never exceeds 50%. And even when the RAN is fully saturated, we have plenty of headroom even on a very low-end device. I now want to turn to some of the production deployments where Magma's been deployed. And I first want to talk about a network deployed by an organization called Access Parks. They deploy a CBRS, or shared spectrum LTE network in national parks, state parks, and so forth around the US. And what they do is they provide fixed wireless service using their cellular network to Wi-Fi hotspots that end users then connect to. And so this is kind of like the Air 1 network that I talked about in Peru. And they ran a pilot with Magma where they had existing LTE networks. They deployed 14 sites and around 200 hotspots using Magma. And while Magma was able to work successfully, which was really exciting for us, the thing we were most excited to see is actually reduce their per site costs by almost 43%. And this was largely driven by some of the operational simplification that we get from moving to this more software-defined approach and having our hierarchical control plane automating the installation kind of configuration of their access gateways at each site. They no longer had to send an LTE engineer out for every new installation they did. The largest deployment using Magma that we're aware of is through an organization called FreedomFi. So FreedomFi kind of runs the Helium 5G or Helium mobile network that some of you may be familiar with. And what the Helium mobile network is about is it's a decentralized wireless cellular network where people are incentivized to deploy cellular radios using cryptocurrency tokens and so forth. The Helium 5G network is a neutral host network, so that means it doesn't have any direct customers of its own, but instead allows users of other carriers to roam onto it on a wholesale basis. This is a really interesting and different business model. Using Magma, FreedomFi was able to deploy more than 5,000 access gateways in less than 5 months. And at peak, they were adding over 150 of these per week. The only infrastructure that they were actually paying for was the orchestrator. And for this kind of a network of this scale, they were spending around $4,000 a month on a combination of bare metal servers and AWS to actually run the services, which is far less than a traditional core would cost. And today, this network supports more than 8,000 radios in more than 49 states, or in 49 states. So Magma, of course, has a number of challenges. So on the 3GPP control plane side, we have continued to have issues with kind of low attach rates that we can support within Magma. And we can solve this, like we talk about in the paper, with larger access gateways. And we think that this is mostly an engineering artifact of the particular RAN-specific kind of implementation we have of the LTE MME that we started with. Magma also lacks wide area mobility support. So if you have a bunch of radios attached to a single access gateway, Magma handles standards compliant mobility with no problem. But if your user wants to move between access gateways, we currently don't support that, and it's much more complicated to support in a fully distributed environment. What we found surprising is there's a lot of use cases where you want to use cellular radios, but you don't actually need mobility. And that's where we've seen Magma kind of take off and enable a large class of new operators. And from building on prior work from Cellbricks, that Jihong mentioned earlier, was built on top of Magma, it seems like now might be a time to revisit these assumptions that the network should actually be what's supporting mobility as opposed to handling that in end hosts. And from a practical perspective, actually deploying new core infrastructure with commercial operators is really hard. It can take over a year to complete testing and interoperability testing with new operators to add Magma to their existing network. And this is complicated by market incentives that incumbent vendors have to make integrating alternative core networks with their infrastructure difficult. And so to wrap up, today we presented Magma, which is an open distributed cellular core network. It's driven by this idea that the choice of radio technology should not define the operator's network architecture. We've achieved separation of a policy-rich software edge from a fast and simple fabric in a cellular context, and we can manage this with a logically centralized control plane. Magma has been able to run on really inexpensive hardware and to support small networks, and it minimizes the barrier to entry for new operators. And we've seen it successfully deployed both in these small networks and at scale in dozens of commercial deployments worldwide. And so with that, happy to take questions and encourage you to check out the website if you'd like to learn more.